who's going to tell us about on the Poisson geometry of isomonodromic tau functions.
Okay, yeah, thanks a lot. And thanks a lot for the invitation to this very nice workshop, which I'm enjoying a lot. When being asked for actually 2 lectures, one being introductory, I thought a little bit how to fulfill this request. So, I mean, what I will try to do is indeed to start off with something that is relatively elementary and which is perhaps a useful piece of knowledge that you can use probably in many different contexts. The price to pay is somehow that the direction where this is going and the connection to some of the topics of this workshop, this will unfold perhaps more slowly than it could have been otherwise. So this here is a kind of self-contained chapter, if you want, of integrable models, classical integrable models, or complex analysis, isomonodromy problem viewed from a Poisson perspective. The exact WKB, which is in the title of the workshop, will come at a crucial point in the second half of this talk. But sort of connections, for example, to BPS states and so on, that will be more the subject of tomorrow's talk, where, for which basically what we're presenting today is going to serve as one important class of examples, or one, to be fully precise, one important example where one can see some of the features. All right. I want to say that this is based on joint work with Joanna, who's in the audience, Pietro, and Ellie. The part tomorrow will also involve Murat, Arpan, and Ivan, who I think were also in the audience. So, but this year is sort of the older stuff that I shall begin with. So yeah, in an attempt to start fairly basic and fairly elementary, I want to introduce things via the classical Riemann-Hilbert problem. And just to keep life simple, I will not make any attempt at, say, any generality. So let's just consider the n-punctured Riemann sphere. So that is this C0n. We take the Riemann sphere, remove endpoints, and that's it. And we get some space which has an non-trivial fundamental group, pi1, which has then n generators, which we can represent by some loops denoted gamma k, which go from a base point y0 on the Riemann surface around these punctures or marked points that we've taken out. Well, that is sort of the topological setup, the topological background of everything else to follow. And the classical Riemann-Hilbert problem, say in a loose sense, we'll make it a little more precise in a moment, is to associate to each of these basic loops a matrix, in our case in GL2C. Well, there's of course a choice here. We could also make SL2C. We could also make SLNC or so, but to be specific, let's talk about GL2C for most of the time. And then, yeah, we can ask for a analytic matrix function such that the analytic continuation along any of these n paths can be represented, or well, more generally along any element of the fundamental group, which you can compose out of these basic paths, is represented by, so that is sort of indicated here. You can see my cursor, the moving thing here. So it's the right multiplication with a matrix that we have associated to that path gamma. In this form, it won't have a unique solution. Let's make it a little more precise to get the uniqueness. So the goal is then to find a matrix function such that the following conditions are satisfied. So that is this psi of y. We want a multivalued and a function which is multivalued, analytic, and invertible on this n-punctured sphere, and which Okay, now I can. And well, satisfies the normalization condition. And secondly, there's a condition that basically implies this condition of fixing monodromies, as we will see in a second, that the psi of y near each of these points where it is allowed to be singular, it has a relatively simple singular behavior of what is called regular type. So there is here some diagonal matrix which tells us how the different matrix elements are, say, allowed to diverge basically when y, which is the argument here, approaches one of the points ck. And there is a matrix ck for each of these singular points, which is a constant matrix representing the basically the normalization, and what remains is holomorphic and invertible at these marked points. So we've just separated out here the leading singular behavior, and what's left is holomorphic and invertible. All right, and then it's clear, I mean, you can basically, with the help of this form, then compute the monodromy action or the analytic continuation of psi of y along a path which goes around this point zk. And you will find that this result here, so when we take here the analytic continuation of psi along gamma k, denoted by this notation, that is represented then by this right multiplication with a GL2C matrix, which we can just compute out of, well, the constant matrix that was here representing this singular behavior and the diagonal one. So it's basically you're conjugating the, well, e to the 2 pi I of this diagonal matrix by the matrix C, and this is what gives you the monodromy matrix. All right, so that makes the Riemann-Hilbert problem rather precise, and in this form, it may for some, so what you choose are these collection of matrices. For some collections of these matrices, it may fail to have a solution, but generically it has a solution, and if it has a solution, then the solution is going to be unique under these conditions. All right. So now, so closely associated is the problem of isomonodromic deformations. Here it's isomonodromic deformations of first order matrix differential equations. And the way this is obtained from the solution of the Riemann-Hilbert problem is as follows. So we fix the solution to the Riemann-Hilbert problem. And what we are going to ask then is, well, a reformulation. I mean, basically, we want to turn it into some local question, namely, so far we've kept these positions Z1 to Zn fixed, and we want to ask ourselves, when we vary them, how does the psi of y vary, or what is then going to be sort of the main player in this reformulation of the problem? We take basically the matrix A of y obtained by, well, differentiating psi with respect to y and then multiplying with the inverse of psi from the right. And if you just look at here this specification of the leading asymptotic behavior, well, you can simply analyze what happens when you form this combination, and if you have y in the vicinity of zk, so you can from this determine in particular that the behavior that this matrix A of y can have at one of these marked points can at most be a simple pole like that. And well, by the assumptions on analyticity, everywhere else it has to be analytic. So this is just what you easily infer from this specification of the regular singular behavior at the point ck, that this is the form that this matrix A of y needs to have. So what you can associate to that is then, well, a matrix first order differential equation of basically the simplest possible form. So the, well, differentiation of psi gives a of y, psi of y. But now sort of we shift attention from psi to a. Well, of course, we can reconstruct one from the other. You may furthermore notice that what this formula also allows you to figure out is, well, how the derivative with respect to zr of psi of y behaves near the singular points. Namely, you can figure out that, well, you can represent the derivative of psi as multiplication with something which is again a function of y, but just from the singular behavior, as when you differentiate here with respect to zk, well, okay, you're producing something which has a first order pole as a function of y at zk. And if you think a little more, you will see that is the only place where the matrix AR of y, which is defined by this equation, is allowed to have a pole. So therefore, you find out that we need to have a second family of differential equation now describing the variations with respect to the points CR that needs to be true. And here, well, the form of these matrices AR of y is a very simple one because there's only a contribution from the pole at ZR. Well, but okay, now from the fact that by definition, basically, everything is coming from a common object, this matrix valued function psi of y, what this tells us is that the system of equation that is obtained by combining these equations 2 and 3 must be consistent. It has a solution, which is exactly our psi. And then, well, you can ask what it means, well, how this can be. Namely, this can only be if the condition from the commutativity of partial derivatives, the partial derivative with respect to y and the partial derivatives with respect to zr, if this holds, partial derivatives, of course, as usual, are supposed to commute. And when you then rewrite it in terms of the right-hand sides here of these equations 2 and 3, you find some equations for consistency that the matrix residues here, AK, have to satisfy. And these take this form of some nonlinear partial differential equations. So when we differentiate AL with respect to ZK, it's something nonlinear, the commutator AK with AL over ZK minus ZL. And there's something similar sort of for the diagonal possibility where we differentiate AK with respect to ZK, where we then get the sum over all possible such terms like here. Now, well, not all possible, the one where L is equal to K is left out here in this sum. These are famous nonlinear partial differential equations, which are known as the Schlesinger equations. And well, they are famous in particular because they are among the few nonlinear partial differential equations where one can say quite a lot about their solution theory. And the fact, I mean, this is in a sense what is called integrability. But on the other hand, the fact that this is so has to do a lot with this relation to the Riemann-Hilbert problem. You could say that the Riemann-Hilbert problem, so a solution to the Riemann-Hilbert problem solves the Schlesinger equations because, well, given that you have a solution to the Riemann-Hilbert problem, which is our matrix valued function psi of y, you just take derivatives like here to get a of y or ar of y, and from that you reconstruct the solution to the Schlesinger equations basically for free. But of course, yeah, what is the hard part is to solve the Riemann-Hilbert problem, which we don't know to do explicitly, but for which there's only proofs of existence of a solution in general. Okay. For us, and to sort of make this even more transparent and specific, to pick out a famous and relatively typical example for this, Yeah, we're doing two things here. We're specializing on the one hand the n-punctured sphere to the 4-punctured sphere. That is this first really non-trivial case where all this theory is indeed highly non-trivial already. And secondly, among these, say, classical systems of partial differential equations related to integrability, there's another one which is basically equivalent thanks to something we will explain in a second to the Schlesinger equation. It's the Garnier system. And the way it comes about basically is, well, we can just observe that we can find a mildly singular matrix function G, which may need to have some square root singularities, but that's not going to be a problem for anything that follows, such that, oh, what I should have written here, I just noticed I've introduced here the notation for a connection nabla. Well, that is just meant to be the connection that whose flat sections are these matrices psi, right? So it is represented exactly by our matrix function A of y as the connection 1 form. This now was abbreviated into nabla lambda. And then, okay, you can consider gauge equivalence of holomorphic connections by holomorphic or almost holomorphic matrices G. And with this, you can notice you can bring the connection 1 form to a very special form. You can produce 2 zeros here and a 1 there. And then all that was in the connection 1 form, the matrix function A of y, is going to be packaged into just a single function that we denote here with a QH bar. And I noticed another typo I should have introduced, which I could have done just by a scaling of a parameter each bar already here. So sorry, there's some typos or not completely, well, incomplete definitions, but in any way, I hope the idea is clear. So, and yeah, what you see here is that this matrix QH bar of X, it is formed out of the matrix elements. So it does not contain any new information. It is just a sort of, well, combination of the matrix elements of this connection 1 form A that we started from. But there's some interesting things that happen on the way. In particular, for example, you divide here by A minus, which is the lower left off diagonal element. So in particular, even if, as we had assumed, the A is holomorphic on all the n-punctured sphere, this QH bar will not be any longer. It will have additional poles at the zeros of A minus. But okay, I can't really sort of tell you the full story here. The upshot is that indeed there is an equivalence, basically a one-to-one correspondence between the matrix functions A of y of this form, which appear in the context of the Schlesinger system, so whose residues satisfy the equations of the Schlesinger system, and then these just ordinary functions, holomorphic, well, meromorphic functions, QH bar of X, which appear here. I mean, one way is, I think, pretty plain and explicit, but on the other hand, well, what you can perhaps imagine is that these here are characterized by the additional, say, poles that the QH bar is allowed to have, and you can sort of reconstruct the G from the idea that it should kill by sort of returning to a purely holomorphic, purely holomorphic on C0n matrix function A of y, the additional poles that are coming here from the necessity to divide by A minus. But well, just to make these all very concrete, let us just write out how such a QH bar of X will look like in the case where n equals to 4. So then, well, if you look a little bit, you see that if A was allowed to have first order poles, QH bar is going to have second order poles. These, however, are fixed by basically the behavior of AR at the punctures for which we are going to fix the eigenvalues. And the eigenvalues are going to determine then the parameters delta 1 here. So these will be for us fixed parameters that we keep fixed once and for all. So this is not going to be the dependence we care most about, although of course this dependence can be interesting in its own right. So the deltas here are coming from eigenvalues of the residues, and we consider them as parameters. And this is what basically fixes, well, these the coefficients of second order poles at 0. Well, here we have picked a specific choice, which is often done, which we can always do thanks to the projective invariance. So one of the puncture is at 0, one is at z, one is at 1, and one is at infinity. That is sort of what we can always achieve with the help of SL to C transformations. And this is a specific choice that is just adopted for convenience. But in essence, thanks to projective invariance, it is without loss of generality. We can always return to more generic situations with the help of just group transformations or Möbius transformations, to be precise. Anyway, the interesting dependencies are here. So what we see there is, okay, here is well, something which is singular at x equals to z. Well, there's a second order term, there's a first order pole at z. It has an interesting coefficient, which we will care a lot about. But then there's an extra singularity, which is really extra. This is coming from, in this procedure here, by going from Schlesinger to Garnier by gauge transformation. This would be one of the zeros of this A minus. Well, the only zero that we have in the case n equals to 4 if we do the counting. And this singularity is what is called an apparent singularity. There's also something, but with a very specific coefficient, second order pole at U. And yeah, the key data here, the key sort of parameters, which are sort of the freedom, the dynamical variables are going to be U and V, because this is what specifies, basically having fixed the deltas, that is what specifies all that is unknown here in the function QH bar, where we use something that, well, you just will have to accept now without a proof. We're using that this function H, which is coming from a procedure like this is not an arbitrary parameter that appears in this. It will actually be a very specific function of U and V and all the other parameters, which we just suppress in notations now, which ensures, I mean, which is fixed, if you know about this, by the property that this is an apparent singularity, which, however, is simply equivalent to the statement that the singularity at x equals to U that we see here is basically an artifact of this gauge transformation G from an ordinary holomorphic connection to something that has a standard form, but which is meromorphic. It has additional poles. So this is what, on the one hand, ensures two things: the monodromy of this, well, of the second order differential, well, this, the monodromy, say, of this connection, which is of course the same as the monodromy of this connection around this point x equals to U, will be minus the identity. That is one way of defining what it means that you have a apparent singularity. So this is unlike the other singularities where you can have a generic type of monodromy around the punctures. So this was exactly what was then specified by these matrices MR. Here, however, around this extra singularity, we only have minus identity as a possible monodromy. Good. To cut the long story short, what we have is basically a reformulation of the Schlesinger equation into a system of equations. So this is just what follows from this construction. It is a reformulation of the Schlesinger equation into nonlinear partial differential equations on U and V, now considered to be as a function of Z. That is the only sort of, well, that is now having fixed three punctures at 0, 1, and infinity. There is a fourth one, which we consider movable. And then we can ask, okay, how do we need to change U and V in such a way. So when we want to vary the fourth puncture, which is at z, how do we need to vary u and v in such a way that the monodromy of this second order differential operator or second order differential equation defined by this operator stays constant under a variation of z. This, well, if you just go back, is equivalent to the monodromy of this particular connection to stay constant. So this is nothing but a rewriting of Schlesinger's equation in different variables, and the variables to be kept in mind are u and v. How about the h? Well, the h is a nice guy because it allows us, so h is a specific function, which here is written out in full glory. It's just a function of u and v, right? U and v are now our dynamical variables, which we want to compute how u and v depend on z in such a way that the monodromy of this guy, or equivalently the monodromy of this connection here, stays constant. And yeah, what has been found basically by the classics already is that, and there was important work of Okamoto well, not so long ago, that these partial differential equations, which are basically just restatement of the Schlesinger equations, in these variables take a nice form, which is a Hamiltonian form, namely the derivative of u with respect to z is the derivative of this function h with respect to p. And well, here likewise with v with respect to z is minus the derivative of h with respect to u. So you see this skew structure that is characteristic for, well, Poisson or Hamiltonian formalism.
Joerg, may I just interrupt? There's a question in the chat actually. That
yeah, I don't see the chat.
That's okay, but I can relay it. But is there a typo there? Should it be dh by dv?
dh by dv, that is right. Thanks. Absolutely, there's a typo here. This should be v instead of p. Thanks. Good. Yeah, and just having found that it is representable in this form, you can invent a Poisson structure which basically allows you to cast this dynamical system into the framework of, say, Poisson-geometry. And that is sort of the simplest one you can think. So this Poisson bracket computed of u and v would be 1. And with this, you can write basically then the right-hand sides here as Poisson brackets of h with the respective variables to which you take the derivatives here. All right, and of course, well, we can here, I mean, sometimes it is interesting to keep in mind that we have these extra parameters which describe eigenvalues at punctures, delta 1 to delta 4. So let's not completely forget about them. So that is here sort of the parameters when having fixed, to be precise, the position of this movable puncture z. But of course, the game is now to ask what the variation with respect to this puncture is. All right, and well, we can of course trivially extend the Poisson bracket to this space of parameters. The deltas would then just be Casimirs, they would commute with everybody else. But that is of course okay in the Poisson world. We could, on the other hand, and we shall do this at a given point, fix the parameters to some fixed values, that is, consider what is called the symplectic leaves, where then we have just the parameters u and v left, and then we are in the symplectic situation. Okay, that is relatively standard. I hope this is clear and does not lead to confusions. It's sometimes necessary sort of to switch a little bit between these different points of view. Well, maybe not necessary, but convenient at least. Good. So you can rewrite this here, and okay, I shall not do this explicitly, but if I can assert you that these equations here imply the famous Ponnevis 6 equation. And by definition, by the construction, by the relation to the Riemann-Hilbert problem, it ensures that the monodromy data are staying fixed when we are considering functions u of z and v of z satisfying these equations, or the Pont-Levis equation. So the monodromy data serve the task, to be constants of the motion. So they label different solutions to the Pont-Levis 6 equation. Different solutions are distinguished by the monodromy data, which we can either represent through these matrices C and D, specifying the singular behavior at the singularities, or by the combinations, I will come to this in a moment, these combinations MR, which represent really the monodromies around punctures. There's a redundancy here in this representation, but okay, we will eliminate it in a second. Okay, so yeah, okay, well, the first thing, and sort of that was the first, the goal of this part of the talk was to arrive at a main definition, I mean, the definition of the tau function. It's basically a potential for this Hamiltonian function. So we can take here our u, our solution u of z and u, v of z and u of a Pont-Levis 6 equation, and then can, by basically integrating this equation with respect to z, define the tau function, which is, okay, by its definition, a function of z and of the monodromy data, because, yeah, here on the right-hand side, I can pick different solutions distinguished by different monodromy data to evaluate here the Hamiltonian. And what you see is, of course, if you have found a tau function satisfying this condition, then you could multiply it with any function of the monodromy data, the matrix elements, say, of these matrices C and D, you will get another tau function, because the z derivative doesn't see any of the data contained in u. So it doesn't, so I mean, this way of defining the tau function does not fix the dependence on the monodromy data at all. And it's in some sense a long-standing problem. Well, depending on whether you see it as a problem or a feature, to find natural ways to fix the monodromy dependence of the tau function. And that's in some sense what the rest of the talk is about, namely to formulate a proposal or key elements of a proposal for how to fix it in a natural way.
Excuse me, should it be log tau or tau?
Oh, I meant to write log tau. Yes, thank you. Of course, yes, another typo. Okay, I should probably, before the slides go anywhere, have a go on fixing these typos. That was perhaps low. Yes.
Sorry, another question. I guess generically there will be several z's. Yeah.
Z's, yeah, Z was here just a single one, because we're in the specific case of n equals to 4, where thanks to the Möbius invariance, only one of the positions of the punctures really matters.
Yeah.
So in the generic case, you would have here a system of equations where you have the partial derivatives with respect to different ZRs that have appeared here in the beginning, or ZKs.
And then what ensures the integrability of these equations, namely that there is a
yes,
function?
Thank you. That's the Schlesinger equations themselves. They serve as the integrability condition. So this will be defined, will be integrable exactly when the Schlesinger equations hold. Okay.
Okay, thanks.
Okay, so the next sort of subsection here of this talk is to talk about monodromies. Namely, we now have to think about a little more and in more detail about what's the space of these monodromy data, the space of the monodromies that we work on, and maybe how to parameterize it, how to define natural coordinates on it. And yeah, here I will have to be at some places very schematic. I hope you will apologize. Yeah, there are some main points I want to stress, but this is of course a whole, I mean, in some sense, a whole direction of mathematics in its own right. Good. Let us note a few simple things that are, of course, very easy and classical, but important in this context. So we can, well, the solution to Schlesinger's equations, I mentioned this already, from the solution to the Riemann-Hilbert problem by taking this combination of derivative with a psi inverse. And what you see from that, this is why I'm writing it down again, is that if you multiply psi from the right with a constant matrix, well, the derivative won't see it, so it won't change A of y. So therefore, but on the other hand, it will change the monodromies by overall conjugation. So therefore, in this context, it is natural not to consider sort of the collection of monodromy matrices, of which we have n in general, as the data of interest, but rather to consider them up to conjugation. So it's a little schematic here. It means up to individual conjugation of each of these matrices mk with one and the same constant matrix in GL2C. So there is, on the other hand, just from the relation in the fundamental group of the n-punctured sphere, a relation that these n matrices always have to satisfy. So in essence, of course, there are n-1 independent such matrices generically that we are interested in. But these are identified, I mean, collections of these n-1 matrices are identified if and only if they are related by this overall conjugation. Yeah, and the space of, which is defined thereby, this quotient space is called the character variety. And that is in some sense a natural definition for what you call the space of monodromy data, or the space of initial values, or the space of solutions for Schlesinger's equations. So this really, well, parameterizes inequivalent solutions to Schlesinger's equations. Okay, and these spaces have been subject to a lot of mathematical study, and they have interesting extra structure. And what is of interest for us here is the structure basically as algebraic Poisson variety. I don't have the time to explain, but there is a beautiful sort of topological origin of both algebraic structure on the space of monodromy data, as well as Poisson structure. We will see a kind of shadow of this in a moment. Okay, so we said we don't care about how things change under conjugation. So therefore, what are natural coordinates to put on this character variety on the space of monodromy data are trace functions, because they're unchanged under conjugation. So this is what we call the trace functions. And well, the upshot in a nutshell is that the trace function describe indeed the structure as an algebraic variety of the character variety in a way we make explicit in our favorite example here. It has a name in the literature. It's called the Klein cubic, because yeah, we have, okay, if you just make a count, you can convince yourself there are some trace functions which give, well, if you just take the traces of the monodromies around the punctures themselves, this will be fixed basically by the same data as we kept fixed from the beginning, which is then packaged into the delta 1, I mean, which is just the eigenvalues of these matrix residues AR. I'm not completely careful here about sort of how these different, well, notations relate, but yeah, it's the same data. And so these we consider as fixed data once and for all. So these are just, say, if you want to be simple-minded, these are just fixed numbers, and we consider everything sort of fibered over some choice of these numbers. Then the interesting things are monodromies around pairs of punctures. So, well, there's here basically three non-trivial independent choices. We can go around the pair of puncture 1 and 2, or 1 and 3, or 2 and 3. So we just in the different ways sort of to pair the 4 punctures into 2 pairs. And this defines functions, which are, of course, by definition, their conjugation invariant. These are functions on the character variety. We call them S, T, and U. So these are coordinates on our character variety, right? So we just use them. And then, well, it's a relatively elementary exercise that using the relations in the fundamental group and relations, standard relations by 2x2 matrices, that we have one relation among the three complex numbers that are defined in this way, and that is written here. So it can be written as the vanishing of a polynomial. The explicit form of the polynomial is here, and we see in the coefficients these numbers that are attached to the punctures appearing as numbers, as parameters. And sort of somewhat magically, so this is okay. So here we explicitly write down, some in C to the cubed, a equation, an algebraic equation. So this defines a two-dimensional algebraic variety. And ST and U are the generators of the ring of algebraic functions, etc., etc. So this defines algebraic structure. And on top of that, we have a Poisson structure, a natural one. And good, that of course requires more discussion. But in a nutshell, what you can quickly observe is, after some computations, the Poisson bracket between these basic coordinate functions st and u, it is also expressible in terms of the same polynomial p by taking a partial derivative. So with this, you have also defined a Poisson structure on this character variety. So these are the two main structures that will be important for us in the rest. Okay, so and then the story, the whole story opens up of how to introduce, how to basically parameterize in a more convenient way. I mean, here it's described as the solution to some nonlinear equation, the points on the character variety, that is to introduce coordinates, which may be even simpler in some respects for the character variety. And there are of course zillions of ways of introducing coordinates as usual, but some ways are better than others. And what can be distinguishing features of choices of coordinates, which is choices of parameters for these trace functions L or L gamma, will be is a simplicity of analytic properties. So we're looking, for example, here for the trace function parameterized as L gamma of two new variables, sigma and eta, whereas the dependence on sigma and eta is as nice as possible. So rational or even Laurent polynomial seems to be the best that we can get. If, on the other hand, we want that the Poisson bracket, which is somewhat complicated here, becomes as simple as possible in terms of the coordinates sigma and eta. And there's another typo to be repaired here. This was meant to be the Poisson bracket, sigma bracket with eta equals to 1. So I apologize for some things which were the result of finishing my slides a little late. Good, I shall repair them and maybe resubmit. All right, and there are some famous systems of coordinates which basically do exactly this with some maybe twists and turns and so on, but essentially you can use them to do the job. But yes, here, I mean, it would be lectures, it would deserve a lecture of its own to explain all this, so I just want to give you the flavor. There are one set of coordinates which are called Fock-Gontroff coordinates, where you associate coordinates capital XE to edges of a triangulation. So you think of, so for example, this picture is a little better. So you think of maybe here in the corner of this, diamond, this should be identified with a punctures. Like we had 4 punctures for the Pont-Levis case. So these would be the corners. And then, if you draw the lines like here, you can define and another one, say, you can define a triangulation of the 4 punctured sphere. And then what one does is, the way the game works is to associate one complex number to each of the edges of such a triangulation. There are some relations between them and so on. There's a little bit of a story how sort of to reduce it to the 2 coordinates that correspond to, say, fixing the parameters at the punctures, but I don't want to talk about this. What is important for the following is that if you change the triangulation, it will induce a change of the coordinates. And in the, say, simplest possible situation, or one of the simplest possible situations that you can imagine. So this here is meant to be a part of our triangulation, where we have a coordinate x associated to this side, a coordinate y to this side. And well, this is meant to be some annulus that we can embed, say, in the 4-punctured sphere. For example, it can be an annulus inserted between puncture 1, puncture 2, and the rest. Then, well, there's an identification which rolls up this here to an annulus, where then the shaded things is the rest of the surface that we are that we're not depicting. And then, yeah, you can have triangulations which look like this, with x and y being 2 of many coordinates that are of this type in this situation. And the point is here simply to observe this very simple change of coordinates that describes a change of triangulation. Okay, so it is of a simple rational form. Yeah, the other important thing is this subtraction free. So this is called, well, a cluster mutation, but this is just for those who, well, know about this story. I just want to mention, so here, well, we have, in general, if you make the count, you would have 6 edges representing say, a triangulation. There would be 6 coordinates. Then there are 4 constraints from fixing the parameters around punctures. One would be left with 2 remaining variables. There's a relatively elegant way that I have not the time to explain to introduce Darboux coordinates in this context, which was used by Kashav in the context of Teichmüller theory or quantum Teichmüller theory, which uses decorated triangulation. So his main observation was that if you decorate the triangulation by marking a corner in each triangle, then indeed you have a way to introduce Darboux coordinates from which you can reconstruct the Fock-Gontrov coordinates by a simple recipe. And yeah, last not least, there is a recipe called traffic rules to reconstruct the trace function from these Fock-Gontrov coordinates. And for example, in a situation like this, it would give something simple, but the formulae can be much more complicated. We would have a formula like this expressing the trace function, which are the, say, good global coordinates on the character variety in terms of the Fock-Gontrov coordinates. So it can look like this or much more complicated, but the common feature is Laurent polynomiality and subtraction freeness. There's always be pluses there. That is a key feature called cluster structure underlying these type of coordinates. I notice that I'm maybe, well, proceeding somewhat slowly. Anyway, I want to mention briefly another set of coordinates which are of importance in this context, which are Fenchel-Nielsen type coordinates. The terminology comes from the fact that they are relatives of the classical Fenchel-Nielsen coordinates for the Teichmüller spaces. They share the feature that they're associated to Pan's decomposition instead of triangulations. But they're not exactly the complexification of the Fenchel-Nielsen coordinates for the Teichmüller spaces in some, because in some sense, these guys we're going to talk about are even nicer than just complexifying Fenchel-Nielsen. And the point is exactly having to do with when we think about how to write trace functions in terms of these types of coordinates, which in some sense, of course, you could do to define them. Namely, you could define these coordinates by just writing down formulae for st and u as a function of these coordinates x and y, capital X and capital Y, which will then, in the case of Fenchel-Nielsen coordinates, take a form like here. So there's something simple for one of the trace functions, which is really extremely simple. The price to pay is the rest will be more complicated. So there will be rational functions here of x appearing in a decomposition into powers of y in this parametrization. And this is a representative example of, well, a collection of others, but it's a discrete number of choices that we're down to, when we impose, say, nice features like that these coefficients here are really rational functions, and you see the denominators are even very simple and they have a kind of universal feature. And then sort of the parameters associated punctures, there are p here somewhere scattered in the formulae and so on. All these are details that of course are impossible to digest in the short time, but I want to give you the flavor. One point maybe, which is a little bit a side remark, but yet I think it's important to stress, say the Fock-Goncharov and the Fenchel-Newton type coordinates, they're less different than, I mean, they're not sort of from different planets. In the end, I think you should better think of them as being closely related. There is a sense in which the Fenchel-Newton coordinates are limits of Fock-Goncharov coordinates after an infinite sequence of, say, flips of this type. That makes some sense, and perhaps it then, so for example, it instructs us to think of these here in some expansion in powers of x. Actually, well, maybe for later, I wanted to ask Pierrick if this rings a bell here, in particular the formula of C minus. Maybe there is an even simpler way, which I don't understand yet, to bring BPS states for of a certain type of a certain class S theory into the game just from these formulae. I leave it for discussions later. Let me take a breath and summarize sort of the main, basically new results of our work I want to present here on this slide, basically in a kind of nutshell. And that will then be sort of introducing already some players that will be important tomorrow. Namely, what we are going to claim is there is going to be distinguished normalizations, that is, distinguished choices of the monodromy dependence of the tau functions, which satisfy a list of properties which on first sight may not be so illuminating, but perhaps it indicates already that there's some interesting structure behind. And this is in some sense the main point I wanted to get to, namely that there is, from the problem to normalize tau functions naturally, some pretty nice structure emerging, which is the following. So the normalizations, well, they fix then the dependence on monodromy data that is in a particular set of Dabou coordinates. Or what I should have said, okay, what you should have kept in mind is we are always sort of switching in between some coordinates sigma and eta, which have this simple Poisson bracket equals to 1, and capital X and Y, which have, well, slightly less simple Poisson brackets, but still extremely simple. So between the sort of exponential world and the logarithmic world. So that may be worth keeping in mind. And so then what we're after are functions with respect to sigma and eta, which satisfy these kind of nice properties. So this is, it looks like generating functions in a sense, and I believe there's more to it, but yeah, we're gonna have to wait a little bit if we can understand this. So if we shift sigma by unit 1, the tau function properly normalized, it would give the corresponding eta. And on the other hand, the thing is periodic with respect to eta. Probably not yet too illuminating, but I will elaborate a little bit what it implies and what it means on the way. So this is, of course, well, for a choice of Dabou coordinates, but there are many of this type. Still, I mean, having narrowed it down to the nice Dabou coordinates, which have the nice analytic and Poisson analytic properties and Poisson brackets, reduce it considerably. But of course, there's a remaining choice, which we will have to talk about. Now, well, of course, from this point of view, it's very natural to ask what happens when we change Dabou coordinates. The claim is that these normalizations, they hang together in the nicest possible way. Namely, the different normalizations are represented, are related to each other by what we want to call difference generating functions. So it's just multiplication with a function. Note we have here always a kind of choice of polarization. We have a sigma and a eta coordinate, which appear a little asymmetrically. So it's periodic with respect to eta. but sort of the periodicity with respect to sigma is twisted by this eta factor. So we pick sort of those which, well, the sigma type variables in the two coordinate systems, sigma and sigma prime. And we are to find, and I will talk about this in a moment, functions of sigma and sigma prime, which are sort of satisfying a finite difference version of the defining properties of a generating function. Namely, if I shift sigma by 1, the eta comes out. If I shift sigma prime by 1, the eta prime comes out. So this is sort of a very, well, rigid and in a sense remarkable in its own right structure that's our claim, governs sort of the good normalizations, a good class of normalizations for the tau functions. Okay, so I mean, I'm anticipating in some sense a lot, but okay, I will hope, I'm jumping here a little bit into the cold water, but I hope I can unfold at least a few of the mysterious things about this a little later. Let me stress, well, good. Of course, here already you can have the idea, good, sigma and eta, you cannot in general expect them to be global. They were going to be defined on just some charts, some parts of the character variety, and sigma and eta prime generically on another one. Natural idea to have could be that this here should then define basically a line bundle on the character variety, a natural one, where we interpret these here as the transition functions because it's a natural function associated to overlaps on to the parts of the character variety on which both sigma eta and sigma prime eta prime are defined. And yeah, then from this point of view, the tau function would appear as a local section of the holomorphic line bundle defined by the generating functions phi. Ooh, I am doing badly on time. So, okay, I mean, in some sense, of course, the advantage of having two talks is I can stop any time. You can stop me any time and I can just continue with what is left over. But yeah, I would need perhaps an indication of from the organizers how long you want me to go on here in this direction. I want now to make a few remarks and present an example for these different generating functions as next steps.
Don't be stressed about time, Joerg, you'll be fine.
Sorry, if I stop now.
No, don't worry about time. I think we'll be fine. So
okay, okay. I go on a little bit and may ask again, or you just stop me brutally. I don't mind. It's either way, it's fine for me. Good. Comments about this. I mean, I understand it comes a little like falling down from somewhere. I don't know where. But a few comments may already help a little bit. So I later, that is a preview, want to relate these distinguished coordinates which are doing this job to exact WKB. That is going to be one of the claims that these coordinates sigma and eta have a natural or a natural relation to exact WKB. Second, well, that is perhaps one of the most interesting remarks at this stage. So having this system of difference equations satisfied with respect to the monodromy dependence of the tau functions, what it basically is equivalent to, because, well, with periodicity with respect to one variable, right? This, of course, makes you want to represent the eta dependence in a Fourier series. So that is what implies part of this structure already, namely that the tau function has a Fourier series expansion of this form. But then taking into account the second equation where the eta appears, that tells you that the Fourier coefficients must have a specific structure. They can be represented as the shifts of the sigma variable of a single function. So basically, the system of finite difference equations is equivalent to the existence of expansions of this type. For basically whatever good coordinates sigma and eta we're considering, this is true. All right, so here comes, well, something that I want to mention, but don't want to elaborate here in this talk. What is part of our claims is that if we choose here Fn type coordinates, then we know a lot more about the coefficients which appear in these Fourier series or generalized to theta series expansions, like in Formula 7. And that, I think, well, that is the basis for, I think, a lot of the deeper statements that we can make about tau functions. So in particular, it is known, thanks to very important work going back to the paper of Gamayun, Yorgov, and Lisovy, that these guys here are conformal blocks of the Resoro algebra at c equals to 1. Closely related is their interpretation as Nekrasov partition functions, which were, well, Nekrasov-Ukunkov had formulae of a similar type already long ago, but I don't think they hadn't quite sort of the geometry related to character variety and so on already at that time. But there is more recent work by Nekrasov and his collaborators where part of this structure is also studied and related to gauge theory, and there's a lot of interesting things around this as well. It can be represented as Fredholm. No, oh, actually, sorry. No, here, this is just written, just wrong as written. The tau can be related to Fredholm determinants, and this expansion can be related to expansion of Fredholm determinants over minors. And that is beautiful work of Lisovy, Gavrilenko, and generalized by Carfasso, Lisovy, and Gavrilenko. And what is bringing us sort of to the next talk, that is tomorrow's talk, is then the observation that we've made kind of experimentally, that these guys here on the left-hand side also are related to limits of topological string partition function, or topological string partition functions themselves, that you can compute with the topological vertex method for certain toric Calabi-Yaus. So there's, it relates to a lot here, this expansion and these coefficients. That holds for Fn type coordinates. That is part of our claim. What we do claim, however, is that there do exist expansions of this type if eta and sigma are related to Fg type coordinates. What we don't know then, and that I think would be a very important question for the future, is what's the meaning of the z's in that case? So we do know that such expansions exist, defining implicitly basically function z for Goncharov type of coordinates, but we don't know what they are. I mean, we don't have, in the sense of having an alternative way of defining, computing, or representing them when sigma and eta are coming from Goncharov coordinates. Okay. Here, maybe I can be quick. So difference generating functions, maybe we can have a quick look at one of the basic examples, which is sort of exactly sort of the flip, which we briefly looked at when we introduced Goncharov coordinates. So how would they look like in this case? So we can then, and maybe, well, you can amuse yourself maybe later walking through these computations. This is all pretty elementary. So we write down the two coordinates in the sort of exponential notations. We write the change of coordinates and solve them then in such a way that we express everything in terms of x and x prime. So the usual business for a generating function. And then we find a system of difference equations for the phi, which will basically involve here on the right-hand side something like this here, right? So this is what appears here on that right-hand side. We substitute here the right-hand side of this. And then we need to solve it. And it's not so hard to solve it if you know the Barnes G function. I mean, it's a certain combination of Barnes G functions which does the job. And that is sort of, well, the typical structure that you should have in mind when thinking about these difference generating functions for the Goncharov changes of coordinates. All right, I can quickly make a few remarks about the strategy for the proof of this claim. I'm not really happy, sort of, I mean, towards the end of today, or well, rather perhaps in the beginning of tomorrow, I can make some more comments on perhaps what could be a more conceptual way of understanding our claim using a possible or emerging relation between tau functions and generating functions for the monodromy map itself. But for the moment, well, there's one story which I believe we understand reasonably well, and it's a little like indirect and not yet conceptual enough, but it proceeds as follows. And this one, I think, is a pretty solid one to sort of derive our main claim, where perhaps you may want to see some more details appearing in the future. But yes, I think we have something very solid here to build on. So the point is, well, we start by just deriving these generalized theta series expansion for one particular set of coordinates of Fn type. And that basically is just, I mean, we can, for example, go back to the result of gamma U Joerg of Lissov and whatever, say, improvements or variants came later for this step. So there exists such a thing for a particular choice of coordinates of Fn type that follows just from all this nice work. Now what we then need to pass to the Fock-Gontrov world somehow. And for special choices of triangulations, basically exactly when we have a piece of the triangulation where some annulus appears like here, there's a simple relation between Fock-Gontrov and Fenchel-Nielsen type coordinates. So the y's and x in this formula would be in the Fock-Gontrov world, and u and v would be the Fenchel-Nielsen world. Or precisely, u would be e to the 2 pi I sigma, sigma Fenchel-Nielsen, and v e to the 2 pi I eta Fenchel-Nielsen. So there are simple formulae here, and such a change of coordinates has been studied in the literature before, namely in work related to Pont-Levis 3, but we claim it carries over to Pont-Levis 6 with a good triangulation. So this has been studied in the work of Itz, Lissov, and Tücki. And yeah, the difference generating function has been computed there, which does the job to represent this change of coordinates. So yeah, so that's our, say, door into the world of Fock-Gontrov, knowing that the story works for at least one system of Fenchel-Nielsen coordinates. Well, and then you need to go on. Then you need to construct the most general difference generating function for Fock-Gontrov. And here, well, that's not explicitly written yet, but we can draw on experience that was made in the context of quantum Teichmüller theory, because this gives a nice formalism sort of for how to organize things, and that should carry over without any serious difficulty to this case. So this gives Fock-Gontrov to Fock-Gontrov. But on the other hand, so this is just change of triangulation. On the other hand, there's change of Pans decomposition. Well, that's also then a relatively standard story once we have the main building blocks, and that is provided by very important work of Joerg, of Lissov, and Tücki, because it is essentially reducing, thanks to these combinatorics of Pans decompositions and their changes, to the famous classical connection problem for Pont-Levis 6, which was solved by Joerg, Lissov, Tücki. And so there a conjecture was presented, which was later proved by Itz, Lissov, and Prokhorov. And this provides basically the essential building block, which is the normalization factor. It's this function phi here that appears in this place for the case that sigma and eta is, say, the Fenchel-Nielsen type coordinates for Pans decomposition where you separate puncture 1 and 2 from 3 and 4. And this here would be the Fenchel-Nielsens for Pans decomposition where you separate puncture 2 and 3 from 1 and 4. And so for this, we know the answer, and then the rest is sort of just, well, going for the ride. Good. I'm probably over time, but I can go on a little bit if you want me to. What I want to say is that sort of the good class of coordinates is probably coming from exact WKB. So that will be a brief, very brief summary of how this comes about. But the point is simply that we have the parameter space of our Schlesinger system. And the question is, can we at least, I mean, there can't be a fully canonical choice of one system of coordinates. That's, of course, too much to hope for. But what you can hope for is sort of to split the parameter space into pieces such that there exists a canonical choice in each piece. And this is what exact WKB does for us, as we want to argue, because it basically gives for each piece in the parameter space a preferred choice of Darboux coordinates that we can construct. That is part of our claims. Right. So, okay, should I stop here or maybe what's...
I mean, I guess if you're starting on WKB, maybe it's better to start next time on that. I don't know.
Yeah, okay. That I think it would be a good point maybe to resume next time. So that is sort of then our goal, our starting point for the next time. It would be to explain how exact WKB does the job of splitting. I mean, we will have to be very brief and sketchy, of course, but yeah, to somehow single out some preferred choices of sigma and etas. Good. So let me stop here for now. And yeah.
Okay. Thank you very much. Thanks. So, are there any questions for Joerg? Andy has a question.
Hi, can you hear me okay?
Yeah, I can hear you. A bit faint though.
Ah, I see. Sorry about that. Thanks for that talk. That was great. I have a kind of naive question, which I think I've asked you before, but I forgot the answer. Is there a version of this where you consider not rank 2 connections, but rank 1 connections? So just kind of like GL1 version of the story? And the isomonodromy for those?
It's not going to be terribly interesting, though. So, because, well, yeah, it's a completely abelian situation. The nonlinearity in the isomonodromic problem would be lost. Of course, yeah, you can specify GL1 connections by their monodromy data. But these flows are not going to be interesting. And of course, you know, the flows are going to live just on some simple tori, etc., etc. Yeah, I don't think I have something interesting to offer here.
I was just wondering, when we get to the end of that, is the tau function in that case going to be like a theta function?
Yeah.
Okay.
Indeed. It would probably be the theta function, right?
Okay.
Well. Okay, I mean, in some sense, as you're bringing it up, that's the way I think about here, these tau functions as a deformation by h bar of the theta functions that you would naively get by, say, Hitchin abelianization, right? So it's all going to be deformed by this parameter h bar, or sometimes it's called lambda. If you go really to the limit where h bar goes to 0, well, I have a little unpublished note I could send you where it is found that you would actually reproduce from the tau function the theta function on the fibers of the Hitchin fibration, which would be the one, well, the relevant one for the situation you're looking at. So yeah, the right point of view, I believe, but there's a lot maybe sort of to be written up and studied and proven to make this a full story, is there's abelianization that you know much better than I do. The abelianization should relate, well, at least in the limit h bar going to 0, should explain basically everything and explain the sort of experimental observation that in this limit tau function reduced to theta function on fibers of Hitchin fibration.
Great, thank you.
Any more questions?
I should stop here the share and then I can see people even.
Can I ask a question?
Please do.
Okay, so what qualitative information do you expect from the ratio of tau function in terms of different coordinates?
What information I expect? Yeah, okay, in some sense, yeah, this brings me sort of to a preview of the second talk, right? So the gist of it is what I try to explain is, in some sense, these ratios of tau functions, well, what they're coming from, the information that they carry are essentially really the information about the changes of coordinates between different patches. But this in turn, of course, will bring us to this type of Riemann-Hilbert problems that Tom studies, which then are just defined by a certain spectrum of PPS states. And in the class of examples that this isomonodromic problem is related to, these would be the class S examples that Andy has been talking about. Well, he has explained us what the spectrum of PPS states is, and well, in one way, I think, or in some way, it was in previous talks, the spectrum of PPS states basically governs the changes of coordinates between different systems of coordinates of Poisson-geometry type. So at this point, sort of, yeah, there is information, in fact, I mean, the information about sort of spectrum of PPS states in class S, it goes into changes of coordinates, and the changes of coordinates, of course, determine these the changes of normalization, these multiplicative factors relating the tau function. And we furthermore are, of course, aiming at a relation to this line bundle that Andy has been talking about in his talks. So that's a little bit the direction it wants to go, namely that basically everything is naturally related to, well, some DT invariance. So, I mean, the point of view I have, but maybe now I'm sort of going a little further away from your original question, is that the spectrum of DT invariance, it determines geometry, and that in this sense, it is very close to the way like Tom likes to think about it. Here, in our case, it's the Poisson algebraic geometry of the character variety, which is sort of implicitly reconstructed from these changes of coordinates between different patches. And now what we're asking is, are there some natural sort of objects or functions attached to it? And I think what I'm trying to stress is, yeah, the tau functions are such objects.
Yeah, so the reason I'm asking is also related to the comment that Lisa V made during a talk, now I forget which one, that the DT invariants should essentially be the connection constants of these tau functions. So in other words, what I think I'm trying to understand is that there are two types of connection constants that you are considering, at least. It's the connection between two tau functions on the same with the same coordinates, or the connection constant of the tau function in two different coordinates with two different coordinates.
What I don't understand is what it was referring to when you said the connection constants with only one set of coordinates, because in some sense, the way I think about it, it's really always a change of coordinates involved, right?
No, I just meant that there's one set of connection constant, which is just a change of choice of pair of pants.
Yes,
and
but the choice of pair of pants induces a choice of a change of coordinates, right, between different systems of Fenchel-Nielsen type coordinates.
Yes, but then you have you're going from Fenchel-Nielsen coordinates to Poisson-geometry coordinates. Mm-hmm. So there are two different kinds of connection problems that
Yeah, you see, I think the best way to think about it, this is something that we try to stress, but I think this may need elaboration and further like study, is that really you shouldn't think of Poisson-geometry and Fenchel-Nielsen as being really so different types of coordinates. I think of the Fenchel-Nielsens by now as sort of a completion of the Poisson-geometries by basically the endpoints of infinite sequences of flips. So they're naturally sort of part of the same, say, family of coordinate systems. So, and in this sense, it's perhaps not at all, well, surprising or so that there's a kind of, that they appear in a unified structure in which you can go freely from one to the other. Technically, of course, at this stage and in all that sort of I understand up to now, well, I mean, the changes of coordinates between Fenchel-Nielsen's to Fenchel-Nielsen or Fock-Gonchow to Fenchel-Nielsen, they look somewhat more complicated because, yeah, this somehow is coming from the fact that one has to take these limits to define them over an infinite sequence of flips, so it's perhaps no surprise. Technically, it is more complicated to construct and to find them, and it's Lisovy and collaborators having done great jobs on this part of the story. But yeah, you shouldn't think of them as being very different from each other conceptually, right? Conceptually, I think they are on a very similar footing. That is sort of the point.
Okay.
Can I just jump in with a very quick question, which is just that Andy introduced this Heisenberg line bundle to us yesterday or whenever it was, and your relations to your tau function, your difference relations look a little bit similar, but they're not the same, right? Because they're not symmetric, whereas his were symmetric. You know, like what? Do you know what I mean? I mean, one of the parameters behaves in a different way to the other one.
May I then show you a formula which is on a later slide quickly? So
yeah, that's allowed. Yeah, I think that's
that
allowed.
may help. Yes. Okay, what's that again? So I will be quick because there's a slide basically devoted to this. I'm comparing a little later different bases in the sections of that line bundle. So there is one. So the phi are ours. There was a formula with Barnes functions, and then there's a magic relation between ratio of Barnes functions and dialogues. And then it depends on what you want to split off by just a change of normalization of the tau functions, which corresponds to an equivalence, I mean, just a change of basis in the line bundle, of course, right? So either you can do it with a factor 2 here or without a factor of 2. In one case, you're getting the Rogers dialogue that Andy had. And in the other case, you get also something very interesting, namely you get, instead of difference generating function, you get ordinary generating function for the same change of coordinates. And that, of course, well, certainly has a deep meaning. I mean.
Right. Yeah. Okay. I mean, I think I understand what. Yeah. Or I mean, even just at the level of defining that line bundle on the torus, I guess you could take A cycles and B cycles and write it differently to how Andy wrote it, and then it would look like your one.
So, I mean, yeah, in any case, the claim I would like to put forward, but this is, you see, the status is it is verified in examples, but really to make it a full story and something that you can claim to have proven, further work is required. But I think sort of what we just looked at is the key observation, because it relates it in the case of the flip, right? It's the relation between the line bundles, which is basically a change of normalization or a change of basis in the line bundle. And yeah, it allows you sort of to go between these difference world and the differential world, and it allows you to go between the form that also Boris and Sergey in their work wrote down for these hyperholomorphic line bundle to the one which sort of naturally appears in our context. So on the level of line bundle, I believe it's all down to changes of normalizations. But as I said, to be absolute clear and honest and precise, the level it has right now is, it was verified in an example which I consider typical enough that it makes me dare predicting this will generalize, but it isn't yet a fully worked out story.
Okay, great. If there are no further questions, let's thank Joerg again. Thank you very much.
Thanks.
And let's meet at 10 to, so 5 minutes later than advertised. Yeah, so 10 to 4.